saying that on a few things. We want to start to memorize this identification of circuits. It is two things. One, it's universal in the United States. If you go somewhere else, they use other color coordinating identification system. And all states kind of follow the same identifying system. I don't know the history of how we set this up. The codebook did not get involved. The codebook let us do it. But so they've established a way to identify conductors, and more so, identify the different voltages and the different systems that we have out there. When it comes to wires, because wires are all the same. I'm using number 8 in any voltage system. But how do I identify the 120/240 circuit in the building from the 277/480 or any other voltage that might be out there? All right, so 210.5, you find this in a few sections. You'll find this in Article 310 as well. This comes up. This comes up in Article 215, feeders, because the way we identify feeder wires, also the same. And I don't know, maybe one or two other sections in the code book. Anywhere where you are sizing conductors and installing wires, this is going to come up. So you find it in other sections in the code book as well. Now, what is this pointing out, or what's this about? Well, it's how we're going to identify the grounded conductor, how we identify the grounding, ing, conductor, and how we identify our ungrounded conductors. All right, you should have gone over this in Code A, maybe even an intro, but it's something that we got to keep repeating and making sure, again, because this is something we have to memorize. So I'm going to lay all three of these out. If you want to write these along with me, good to go. Grounded, and I'm going to put here neutral as well, and I'll explain that in a second. Grounding, and then ungrounded. Okay, grounded, ungrounding, or grounded. Actually, and I wanted to put that one here as well. It's always good that we know which wire we're talking about, just a reminder. All right, so these are the three types of conductors that we're going to have in a circuit. We're going to have hots, sometimes neutrals, and almost always in a conduit or cabling system we'll have a grounding conductor. Although the code book sometimes does allow you, not sometimes, it does allow you to use a metal conduit as the grounding conductor. EMT is allowed to do that, but a lot of times building codes will supersede that and say no grounding conductor in every conduit. So almost always you're going to find all of these. So see how much you retained. Could anyone tell me what two colors we're allowed to use for our grounded or neutral conductor?
White and gray.
White and gray. White and gray. Very good. All right. Very good. Now, follow-up question. When do we use white and when do we use gray?
What's the question? When do we use white and when do we use gray, right?
Yes. When do we use white and when do we use gray?
Gray is 277.
Very good. It's for the 277. We represent both. Anytime we write them, yes, it's for the 277 circuits in the high voltage world. Never for the 480 volt circuits, because those are not going to be using a neutral. But we always represent both voltages of the system. We always call it a 277 480 volt system. So it's the single phase of the 40. Very good. So that means we use white for the other one, 120, and we represent the voltages 208 and 240. Do not forget 240. I'll slide over because I might be getting in the way. 208 and 240, those two voltages systems that also have the single phase 120. They both share the single phase 120. This gets into a transformer conversation. There are two, and I'll give you a quick breakdown of this. There are two different style transformers out there, represented as such: the Y transformer and the delta transformer. This is nothing special. Sorry, go ahead. Is there a question?
It was Y and delta from before. So.
You guys did talk about this?
A little.
Yeah.
Okay, good. A little is good. That way it's not like for the first time ever and I have to go into further. So good. These are two types of trend. Now, what I meant by nothing special is this is just a design type. A Y designed transformer and a delta designed transformer. Transformers are built with windings, right? A pair of windings. And I have a slight representative of a winding here from a motors piece of component. Zoom in on me. And this is what a winding technically is. This is a coil from this component. It's in here in your contactor. You'll get to these in motors classes. Inside there, in the back of this thing, is this. It's a coil, but windings are sort of the same thing. They're just a single wire, this one's very thin, wrapped around many times, leaving a hollow space. And in the world of transformers, a piece of metal goes in here. And this is how we transfer energy, or how transformers transfer energy, to be able to go from a high voltage to a low voltage or the other direction as well. Windings. So each one of these little squiggly things you see there is a winding. And so a three-phase system has 1, 2, and 3 windings. This one is connected in parallel. Sorry, I stumbled there for a second. The Y is connected in parallel. This means they're independent of each other. And the delta 3 phases are connected in series. They're a series connected transformer. It's the only two ways that you can connect anything in the electrical world, whether we're talking building transformers, wiring up control circuits, designing a PLC, ladder diagram, anything, Christmas lights or lighting circuits, you can only wire things in a parallel or in a series way. That's it. And that's got a bigger explanation to it, because you can show all these different designs, but we're looking at these transformers. You guys looked at a little bit of series and parallel as well. It's how circuits are designed. I'll do the delta first. In the delta transformer, if I have 120 on A phase and 120 on B phase, because it's in series, those two voltages simply add up. So we'll have a 240 volt measurement between any of the two phases, A to C, B to C, or A to B. In a Y transformer, there's a different thing that happens when you wire it up in parallel, which is it doesn't add up anymore. So if I have 120 on A phase and 120 on any of the other phases, I was just looking at a way to write this easier. It doesn't add up anymore. It actually has to get worked out through a number that you may have heard while you were having this conversation, which is the square root of 3, or 1.732. And if you multiply this, it'll come up to 207.9, or what we call 208 volts. It is just the way the transformer is designed. Nothing, like I said, special about either one. The only thing special about the Y transformer, and you'll get deeper into this in code D, is that you get a neutral that doesn't have any issues. So these days the Y transformer has become the most popular out there, used in commercial and resident and industrial buildings. The one in our building, or the school, is a Y-fed transformer building. And how you know you're standing in front of a Y transformer or a delta transformer, I'll go back over to my transformers, is I would just simply measure between two of these. any two, and it will say, in this case, 208. And so I'll go, okay, this is a 208 volt 120 panel, and then I say, like say I measured this one between A and B, and I get 240. So now I know there's a delta transformer out there. Does it matter to me? No, not at all. Going back over to where we were so you can have all this information. This is where our wiring identifiers come into play. You can do the same, by the way. I'm going to erase this. It's on the video. I am recording this, so if you need all that, only because it's for future modules, but anytime we're looking at these numbers, it's good to know where they're coming from. You can do the same thing that I just showed you there from with the 120. You can do this with 277, the other one, where the gray comes in, 1.732 equals 479 .6 or 7, I forget now. Doesn't matter, it's 48. By the way, there's another one out there, especially since you're out in California. They do have this voltage that runs around out there in industrial parks. Large manufacturing facilities will have 600 volts. These are the 3 Y transformers that are out there. 208, 120, 208, 277, 480, much more common in industrial, but also 600 volts. And I had a student way back that worked in an industrial place that they had 600 volts to motors, to large industrial motors.
Big.
Yeah. Scary, right? I've never been around that voltage. We are allowed to work on it. We are allowed to work on that. Not that you would want, like, hey, I'll do it. Yeah, let me get in that 24 volt world. Nice and safe. All right, now for grounds, unless anybody had any extra questions there. Don't want to move away from something that you might. All right, so for grounding, there's only 2 types. This is bare copper, or bare aluminum is fine too. And then green. That one's no voltage, anything. It's just, and so nothing really there that I want to ask about. Okay, now this is where it gets fun, which is in the hot conductors, or the ungrounded conductors. So, this is going to kick us down to this one. All right, so that's what it's telling us. Ungrounded conductors shall be identified in accordance with this below one. 1 and 2, we'll get to 2 in a second. 1 gives us the most part of it. All right, so here's what happens. All right, what happens? Commercial buildings will have, and industrial buildings, commercial and industrial buildings, usually want 480 fed into their building. All right, Ohm's law is why. All right, Ohm's law is why. If I have to connect a motor, if I connect it to 480, when the motor is operating, it draws less amperage. If I connect that same motor to 208, which 3-phase motors allow you to connect to either of the 2 voltages, Ohm's law happens. If I connect to 208, then the amperage goes up. Now, this does not affect the motor, the life of the motor, or anything other than the size wires that I use, and the breakers that I have to use, and the size conduits that I have to use. The higher the amperage, the larger the wire, larger the breakers, larger the conduits. More expensive. So when you have to put up a lot of motors, or again, you're building these large commercial buildings, they'd rather 480. But if you're a commercial building, as I said, you also need low volt, you need outlets, you need to plug in computers and have standard 120. So in the building somewhere, even in multiple places, you'll have transformers that are stepping down a panel that's 480, 277, because that's what you got into the building, because you want the high voltage. This is feeding your HVAC circuits or your air conditioners, your motors, whatever pumps you have in the building, all of that machinery stuff. And then you'll have a transformer. You'll feed a transformer from that panel and then come out to another low, what we call a low voltage panel, 120, 208. And these will feed all of the outlets in the building and etc. So what does that mean? It means this building has 2 different style voltage systems. Now, you're the electrician going into the building. They've asked you for another outlet, so you need to put 120 volts somewhere. You pop open ceiling tiles, you open up a junction box, there's a bunch of wires inside. In that scenario, here's where this code section comes in. Where the premise wiring system has branch circuits supplied from more than one nominal voltage system, as I'm showing you here in this example. I have 12208, I have 48277 in the building somewhere. Each ungrounded conductor of a branch circuit shall be identified by, here's the important part, phase or line, which means the same thing, meaning the A phase, the B phase, and the C phase, and by the voltage system, meaning my wires have to be identified such that when you open up that junction box and you see the colors on the wires, you know phase, you know whether you're looking at an A phase wire, a B phase wire, or a C phase wire, and you'll know whether you're looking at 12208 or 480-277. So that's all the code book says. The code book just says you will represent these two voltage systems and all the individual phases in those circuits, in those systems rather, in different colors. Now, colors you decide. Anything you want on the color spectrum. So what we decided, you probably know them already, but as follows: 120, 208, and 240. Can anyone give me these colors? The A, sorry, hold on. Let me actually add this part too. The A phase, the B phase, and the C phase, and you already had the first one. Go ahead.
Black and red.
Okay, very good. So you have black. This is the one we always get these. Red. How do I represent B phase? Or sorry, C phase now. What color does C phase get here?
Blue.
Blue. Very good. Blue. Excellent. Well done, blue. Black, red, and blue. Very good. And 277, 480. There isn't a third one here. Big long line to get there. Now these colors. Anybody know these colors?
277, 480.
Yeah.
She.
All right. No worries. You can go ahead. Somebody had them.
Orange.
Orange is one of them. Which one is it?
Oh, sorry. Yellow.
Yellow's another one. Good so far.
And brown.
And brown. So brown, orange, and yellow. And like they say at Westminster, in that order. Brown, orange, and yellow. So here is how, when you open up that junction box, you know if you're looking at A phase, B phase, or C phase, or and 120, 208, 240, 277, 480. Memorize this. This is a memorized thing. This is universal. Some exceptions to a few different voltage systems that are out there. All right, there's a transformer called a high lag delta transformer that produces an odd voltage on the B phase. This is just they sometimes represent that one in purple, but we're getting into now odd situations. 99.9% of the time, these are the colors that you'll see out there.
So 277, 480, that would be the industrial, correct?
Industrial and large commercial buildings.
Large commercial.
Yeah, and what I mean by large commercial, I mean the school you're in is considered a commercial building. A Target, a Walmart, large things like that.
Costco?
Costco as well, yeah. And what is a Costco? I mean, they don't have motors, they don't have shipping and receiving and convey, or I mean like distribute, they're not assembling, there's not like a massive production plant. So why would they need? But they have large air conditioning systems, they have refrigerators, they have freezers, they have a bunch of lights that they have to energize, they have sprinkler systems, so they have pumps all around those buildings, outside parking lot lighting. This is Ohm's law. Let me just paint this picture for everybody because you learn Ohm's law, and so you have to know how to understand it in, I could use page here. When I have a lot of wattage, P, all of those lights and motors and refrigerators and freezers and everything that the Costco is going to have equals out a total wattage. This is what we are going to do in week 3. Learn how to determine the total wattage of an occupancy. We will focus on residential, but we can expand this to anything. Costco as well. So Costco's is going to have a bunch of wattage demand. What Costco wants is a high voltage into the building so that they can produce a low amperage. All right, so the wattage, the voltage, and the amperage situation. So the higher the voltage going into the building, the lower the amperage for all of those. So a Costco, the difference from a Costco and an industrial building is a Costco also has a lot of demand for low voltage, 120 for computers and cash registers and everything else, you know. So they got to plug in outlets for all the TVs they sell and all these components if they're going to light stuff like that up or energize these things. So they need 120 a lot as well. So that's why I said, though, commercial buildings are more likely to have 2 voltage systems in the building because of that. Industrial as well, but industrial might have like one little office or 2 offices where a couple of computers are held. They will have a higher demand for higher voltage. All right, now I do have, just to show them here, just a couple of panels that I found really nice, well done, professionally done, have not been tampered with. And here you can notice, unfortunately, it is cut off a little bit, but the neutral down here is identified as white, and the neutral here is identified as gray.
It's very clean.
Yeah, this is very well, very clean. Nice use of tie wraps. All right, throughout everything. The grounding conductors are all tied in nicely. One of the things that you will notice, see if anybody, I mean, it should translate fairly well on screen. And this is what I mean by a lot of what's going on here. If we look at the 2 different style breakers, and it should be clear again, if anything like that is not clear on screen, let me know. But a lot of single pole breakers on this panel. A lot of use for our neutrals in this panel. Lots of neutrals. If you'll look at my higher voltage 480 volt panel, no single pole breakers. They are all either using 2 phases or 3 phases. You will notice not a single neutral other than the main one that comes in. Lights, single phase circuits could have been pulled out of this panel, but you'll notice this panel has all multi-wire brand circuits. All multi-wire brand. Not a single neutral in use. So there's the 2 differences in the 2 ways in which circuits get wired up as well. Right? A lot more use for neutral loads in the 120, 208, 240 volts. And because we see this here, this blue, there we, you know, again, we see the color differences. I was going to say, because we see this blue, but this gets into too deeper of a concept. We know this is Y, we know this is C phase, we know this is 208. It's not 240. 240 would only be hot, 2 hots, red and black. But again, let's not get too far in there because I'd have to show you transformers. All right, now one last thing I do want to point out before we go on to, and it is this just a identifying means, although you should know the identifying means, right? Down here below, number A says how we're gonna, the way in which we identify these. So you can do this in a couple of ways, right? You can have the insulation be the identifying feature, or the way you identify, because you'll notice these on this side, these are all, the whole conductor is one color. Same thing for the smaller conductors here, they're all one color as well. But you'll notice these large conductors coming in on that one, they're using phase tape to identify. Now, this is very expensive to buy an entire large conductor, 250 kc mils, 4/0, these big numbers. Very, very expensive to get the entire conductor as one color. So a lot of times the customers will opt for solid black all the way through with an identifying phase tape, which is what's being pointed out here. Means of identification, tape being the most common. We could tag them. I've never seen tags on, other than big giant conductors might have tags. Color coding, marking, but like I said, most of the time we will use tape. And down here is just talking about accessibility to them. We can ignore posting of identifications doesn't matter for us. All right. So when we look at Article 215, this will come up again. No, we're not going to do all this again, because it's the next article that we'll look at. When we do Article 310, we will also look at this code section, and I'll just remind us of this note. So make sure you have this note, and now make sure, again, we start to just now memorize this color coordinating system that we have. All right, let's drop down to the next code section, unless there's any follow-ups there. We're going to jump down a little bit, 2 pages really it takes us, over to page 80. But we're going to make a quick stop before we get over to 210.7. Sorry about that. We have to stop here at 210.6, which takes us into 210.7. All right, I can't explain 210.7 until we look at 210.6 first. All right, now 210.6 is on the voltage limitations of a branch circuit. Now you will see 2 numbers here on the B and the C. All right, you will see 2 numbers on the B and the C. B is saying that the highest voltage you can have for these components here is 120. And C is saying the highest voltage you can have on, and by the way, all of C is lights. It is all lights, all the way down. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, there's no 9. Lights. So in other words, all of the lighting systems can be a maximum voltage of 277 to ground, meaning hot to ground. Now, they could have said hot to neutral here. It doesn't matter. They've just chosen to express how we would check the voltage in the system, hot to ground. In other words, and it says it right here, when you leave 120 on your lighting circuits, the maximum you can go then on lights is 277. It's really what all of this is saying. In a lighting system, it's either 120 or your lights are going to be 277. We really don't have any voltages in between those. All right, so that's what B and C are talking about. But let's look at A for a second. I jumped A. We'll go back to A for a second.
Hello.
Now what A is saying is, in homes, in dwelling units, in a house, or a guest room, or a guest suite, hotel, motels, and Holiday Inns, the voltage shall not exceed 120 volts on these circuits. These circuits are lights and generally what you would plug into your standard outlets, which is really small motors. If you think of something like a blender or garage door motor or little motors, we don't have a lot of, like a fan, the fan that goes over the oven or range, like all these little small motors. A garbage disposal motor, really small, or really low wattage. That's what you're looking at here, 1440 VA is another way of representing wattage. It is how we would calculate wattage in Ohm's law. Let me just explain that because that's going to come up a few times. Anytime you see volt amps or amperes, what they are saying or what they're talking about here, this is watts. We'll represent this as VA, and what VA means is watts. Because how do we calculate wattage? Well, the way we calculate wattage is multiplying voltage times amperage, and you equal wattage. All right, so if you plug something in that draws 10 amps, and you plug it into a 120 volt circuit, it'll generate about 1200 watts. But this is a calculation. In a calculating world, we don't say watts. We say VA. 120 times 10 amps equals a estimated wattage of 1200. So we would say 1200 VA. Whenever you see VA, you are talking about an estimated number based off of calculations. Now, when you say watts, you're talking about measured energy now. In other words, when I actually plug this thing in with 10 amps, when we measure the wattage or when we measure the energy usage, now we're actually getting a physical, real representation of right now this thing in usage. So that's wattage. So wattage and VA represent the same thing, power, or again, energy. All right, this is what watts are. They're power and energy. Another way to represent that is in VA. By the way, another way to represent that is horsepower. Power, right? Energy. It's how we represent. We're the only country in the world that uses horsepower as a unit of measuring energy. Everywhere else in the world only uses watts. But we don't need horsepower right now. Something you'll get to in motors class. So when you see something like this, and we were going to see a bunch of this stuff in the next Article 220, what this is saying is no more than 1,440 or 1,440 watts can be plugged into this circuit. That's why it's saying cord and plug connected loads of 1,440 watts. Now, if we wanted to know, well, what does that mean? How do I determine what I can plug into this outlet? Well, you would take 1440 and do Ohm's law. And I'll run this real quick just to have a number here through my calculator. 1440 divided by 120. This is about 12 amps. I pause there again just to write if you're writing, but understand, just look at this also and just absorb it. This comes, it's going to follow us around a little bit, this VA representation of watts. All right, so again, watts is power or energy, same. When you're talking about measured, so in other words, the electrical company, when they bill you off of wattage usage, because that's what you're using. They're not billing you off of VA usage. Now, just to kind of finish it, like for customers that are going to buy a light bulb, for example, when you go to buy a light bulb, it doesn't say VA, it says watts, because people don't understand VA. If you put, these days it's all 15, but when I was coming up, it's 75 watts and 100 watt light bulbs, and if you would have put a 100 VA light bulb, everybody would lose their mind. What is that? What does that mean? When you buy a toaster, it tells you wattage. When people buy microwaves, it tells them wattage. But that is not correct. That is just for the consumer. So we get so wrapped up around wattage, so we got to break that understanding as electricians. That microwave is actually 1,000 VA. Watts would be the microwave actually turned on and in use. Now, why is that different? Because of the 120. Measure your outlet. Do you have 120 that you've plugged that microwave in? Are you sure? What if you have anything else? What if you have 110? Well, that number changes now. Right? But if we look at that the other way, if we have now 110 times 12, sorry, that's a terrible 2 there. Same thing, we still have the same amperage, but we changed the voltage. Do we still have the same wattage? We do not. 110 times 12 now is 1,320 watts. So therein lies the difference. When this thing was calculated, it was calculated using 120 volts. When this showed up to the person's house and was plugged into the outlet only had 110. For whatever reason, voltage drop, a lot of issues. So when that device is actually in use, the wattage, the actual energy being used is only 1,320 watts. All right, hopefully that's making sense. So again, you can't call the microwave you can do whatever you want, but technically they should not represent appliances through wattage. They should represent them through VA. But again, customers would not understand that. Consumers would not understand that. So it's why you see a lot more watts then. But when we get into these code sections, the code book doesn't care about that. They will use volt amperes correctly or VA correctly. All right, like I said, it's going to follow us around a lot. In fact, it's going to follow us today as we're going to get into another code section. Okay, so let's round this all out to understand what this is saying in easy to understand terms. 210.6 says outlets in houses, hotels and motels, guest suites, dormitory, things like that. That's why it says similar occupancies. Those outlets can only be 120 volts. All right, your standard outlet. 120 is the max for a house. Remember, lighting circuits. Here's my lighting circuit. There's my light bulb. These can be 120 to 277 max. Commercial buildings will use the higher voltage if they are able to get 480 into the building, which is what they like. Because they have a lot more lights than we do in your house. That's what 210.6 is saying. Now, let's jump over to 210.7 because this is why we couldn't start at 210.7 without looking at 210.6 because 210.7 allows us to use a higher voltage at an outlet in residential. All right, this is what I say about the code book. It always does this. It'll say only this way, and then you'll read another code that says you can do it another way. This is where, again, this is a law book and it gets confusing. All right, so if we're looking at 210, it says for multi, not multi, I meant to say that, multiple branch circuits. So remember what a multiple branch circuit was, is go back to a representation of that. Do I have one? Yes, this is a multiple branch circuit. 2 circuits, one for one series of outlets, 1 circuit for another series of outlets. But what if, let me set up a scenario here, right here on this panel, just so you can understand this. All right, actually, I'll ask it this way. And I'll put this out as a question. Let's say this is a duplex receptacle. And this happens a lot in a house where you'll have the garbage disposal under the sink. Garbage disposal tears up the food, plugged into an outlet. And because we're in the kitchen and because we're right next to the sink, because you got the garbage disposal, you'll have the dishwasher. This is where they place the dishwasher right next to the sink, not far away because it doesn't make sense for the homeowner. And guess what outlet we like to plug this into? Same one. So you'll see a sink, garbage disposal, dishwasher right next to them. Under the sink you have an outlet, both plugged into this. Both are plugged into this. All right, good so far, just so you understand the situation we're in. Now here's my question. How much voltage is at this outlet?
$240.
Asked as a question, but also correct. 240, we have both phases. Very good.
Nice.
So if we look at Article 210.7, that's what this is. 2 or more branch circuits supply devices or equipment, garbage disposal in this case, and dishwasher, on the same yoke or mounting strap, whatever you want to call the thing that holds the two plexes on a duplex. Let me go over now to my article here that I have with some outlets shown. There's the article up above. If two or more, what's that?
Looks fancy.
Yeah. I try to set these up like that. This is recorded too, so it looks good. I'll have the best videos out there.
Oh yeah.
So here's my situation. And by the way, I had a friend that called me with a problem, so I'm gonna place a troubleshooting problem in front of you. So here's what they had. They had one breaker, 20 amps, because it's a kitchen, and we'll look at that. This is in Article 210, gives us this as well, tells us what these outlets have to be, or circuits have to be rated at. So I have two individual 20 amp circuits. I have A phase here, we'll just say that's the A phase one. We have B phase, we'll represent it in B phase color correctly. So first thing to the rule that it's saying. First thing to the rule it's saying is a rule that we've already seen, which is simultaneous disconnecting of the hot conductors coming to this one outlet. If one shuts off, the other one has to shut off. So both breakers, again, either side by side or you got to tandem this situation. Now, if I use two individual breakers like this, then I have, like I said, A phase and B phase going over to this receptacle. So right now, as you're looking at this, at everything that I'm showing you with this outlet, is this legal?
Yes.
Look at everything I have on that board. So now you know the answer is no. So now I'll place it this way. This is not legal right now. So why is this not legal right now? Look at the description of the outlet.
Because they can't be disconnected simultaneously.
No, so let's just say I'm able to, but good point. Yes, I'm putting them side by side, and I'm able to disconnect them both at the same time. So we've covered that. So we've got that part.
It's rated for 125.
Thank you. It is rated. The Leviton receptacle that you see below, duplex white 515R. That's the NEMA number, National Electrical Manufacturers Association. They number all of the receptacles. They number this. They number the way this looks. It's called the configuration. 15 amp. That part's actually okay. I'm not sure. That part's actually okay, but I'll point it out where the code book says it's okay. It's in this section as well. But here, 125 volt rated receptacle. This is no good. You used the wrong receptacle. Inspector will look for that. If they, in the garbage disposal dishwasher world, this receptacle has to be rated for 250 volts. Because we have 120 on A phase here and we have 120 on B phase here, meaning we have 240 at this receptacle. So this is one of the things inspectors look for. By the way, the other reason we know this is 15 amps is there. This is what 20 amps looks like. It doesn't have to be this little sideways one. I just like that one for differences on these two. It can be vertical as well. It doesn't have to be horizontal. So you have both. You have 20 amp outlets that look like this. You should have those kitchens, living rooms, garage, outside outlets. There's a lot of places in which the 20 amp outlet has to be. We'll look at those. This, again, like I said, this article shows us all of that. So 210.7 says we can have circuits with, an outlet can have more than 120 at the outlet as long as both circuits are able to be shut off at the same time. And I'll add this part to it, which is not covered in this article section, and it's about the rating of those receptacles. They do have to be of the rating that is able to handle that for the receptacle. Since I'm not covering it, I just want to mention it because it's part of this article, or at least it's a concept that this article is saying that we could do. Now, here's why my friend contacted me, that this has a tab connecting one plex to the other. Because generally we don't have, generally it's just one circuit going to the outlet. So you don't want to have to put a jumper wire. So it has the connection between the top and the bottom. But in this case, we have the other circuit. So the first thing is you have to break that tab. If not, you are connecting A phase to B phase. All right, and that's initially what he had as a problem. That's what he said. He said, every time I turn on the dishwasher, I lose the breaker to the garbage disposal. I shut off the dishwasher. I turn the breaker back on, turn the garbage disposal on now just to see if it's working. And then it shuts off the breaker to the dishwasher. So it just shut them both off. Now, what is that telling me, by the way? That is telling me that we have no actual, this is the other thing that he had wrong in the house. He couldn't fix this one because whoever wired these up put them in 2 different locations. So he had a lot of issues there too. You can't fix that now. At some point I can fix it for him in the future. It's not that critical, as long as nobody's going to work on that, but there was the problem. That's why he called me up. And I said, is that tab broken? And that's the first thing they saw. The tab was not broken, so. All right, we got some time still. Let me just see where we're heading and make sure. Okay, cool. All right, unless there's any follow-ups there. All right, so a couple things again, just to keep in mind here. Whenever you're buying receptacles, you're gonna want to make sure that their voltage rating is matching what you're wiring up. If you're just wiring up regular receptacles in a house, then 120 is. But here's where people make the mistake. You run into Home Depot, you try to grab an outlet. Just putting in a dishwasher garbage disposal situation, you remember, I'm going to break this tab, no worries. But I want to get that cheapest outlet I need, so you grab the one that is rated for the lower voltage. And yeah, you can certainly fail an inspection with that. I don't think there's anything like damage related wise. I think the receptacle will be fine, but again, it is a code violation in that. Okay. Next section, GFCIs. So same outlets, right? Talking about outlets, multi-wire brand circuit, no rules break. If you're using a GFCI and you're running 2 circuits over to the GFCI, then same thing. You got to make sure the GFCI is rated for 250. They do have them as well. It's going to cost you $35 for one. This one is, by the way, and this is something, again, that you should, there's a lot of, you should start to memorize this that I'll say. So take that, if you're not memorizing it, don't worry. But I'll just say try to, if you can, just those 2 configurations separating 20 and 15. Again, these are things that newer electricians should be able to point out. Obviously, as you're getting better and more school time. But I asked you for a receptacle and you know where we're going, and you know it's supposed to be 20 amps. These are all connections that we should be making. So when we see this GFCI, we should already identify it because of the neutral side being that configuration. This is a 15 amp rated GFCI. And that's important because some GFCIs going into homes, like the one in the garage, or like I said, certain areas of the house have to be 20. So if you buy the 15 you will fail an inspection. All right. You use the wrong size wires, 15 instead of 20 amp wire, all these little things like that. This is where inspections get failed too. Just in buying the wrong receptacle. All right, so GFCIs. There's nothing to this section to really go into other than there is two sides to this section. A talks about residential, what they call it, dwelling units is what we refer to it as, and B is everything else. Any other occupancy that isn't a house or something like a house. Right? They'll always say that, dwelling units, and I believe that gets pointed out. So that's all. And these are all the locations where GFCIs have to be used in those two different style occupancies. In houses, in all of these ones. In other style occupancies, then you'll have different things. So all of these. Whoops. Hard to highlight with this PDF sometimes. All right, where you can have a buffet area, obviously restaurants and things like that. Aquariums or something like that, hotels or bait wells and tackle shops. You have locker rooms, all these different style of things, places, where GFCIs have to be used. But there is a common sense theme around GFCIs, and that is water. Everything you see in both of these sections is related to either water or places that can get flooded. That's the general theme around GFCIs. GFCIs get used anywhere near water. So if you look at all these, they start with bathrooms, right? First ones on both bathrooms, kitchens, garages. Now, is it wet inside? No, but sometimes you have water usage in the garage for whatever reason. Power washers, things like that get used more in there. Flooding, garages can get flooded a lot more. So you have that. Outdoor spaces, crawl spaces like under a house, rooftops and outdoors, all of that. The only thing of note that we do want to highlight in these two sections, other than, because you're going to get a question like, where do I have to use a GFCI? Which of the following requires a GFCI versus not a GFCI? So you'll be able to answer these questions as long as you know these two code sections. The only thing, as I mentioned, to highlight here is there's some distances to look at. Sink, shower. And by the way, these two changed from 3 feet when I was coming up as a young electrician to now 6 feet. This used to be any receptacle within 3 feet from the edge of the bowl or sink. Now it's 6 feet. So want to make sure that you snag that little feature to these two sections. Bathtubs, shower stalls, 6 feet. Now, usually you don't have receptacles this close to these things, but in a kitchen you might. Right? In a bathroom, you probably won't have a receptacle so near the shower unless it's a very small bathroom. Bathrooms will have to have one outlet by code. You have to have one outlet in a bathroom. It could fall within this. But this is why I don't get that. I never got this one. Which is, it's already telling me the bathroom has to have a GFCI. Why are you also telling me near the shower? Isn't this all in the same place? I never got that one, but okay. Okay. Any outlet in a bathroom. But I know why it is. It's that sometimes you have larger. I forget that not everyone has my little tiny bathroom. Some people have a lot of money. And they could potentially have, a shower over here. They could have the vanity over here, an outlet over here. GFCI. Has to be GFCI. The one near the shower over here might. So sometimes people have, I just meant, more than one outlet in a bathroom for reasons of they have a lot of money.
Yeah, they're rich.
Yeah, they're rich. They have a bathroom with 2 outlets?
Man.
What kind of life are you living, man? I don't know that life. I don't know a 2 outlet bathroom life.
You guys have outlets?
All right, like I said, when you get into non-dwelling units, then we have a bunch of other things here. There is a couple of amperages to consider here, but nothing that we need to focus on. But you do see, just to actually point that out, you do see the 120 through 250 volt receptacles, meaning the two different style receptacles that I just pointed out, 120 or 250. No matter what the circuit is concerning itself with, it has to be GFCI. So these days, under the sink, GFCI receptacle for the garbage disposal and the dishwasher, as I mentioned. So you'd have to break these two tabs, which GFCIs have that feature as well. All right, we are getting into some classes about to be done territory, just time frame wise. We're going to skip a lot of this stuff in the auto transformer world here, cross spaces, and then we don't have to worry too much about that. We are going to hang out here tomorrow. Here's where we're going to get started tomorrow, but I do want to kind of preempt this already. All right, do want to get into a quick quick explanation here on this article, which we're going to start tomorrow, 210:11. All right, branch circuits required, because this takes us into the beginning. This is the beginning of a much larger set of calculations. You can see it's mentioning Article 220 here, which that article is called Load Calculations. This Article 220 covers how to determine how much wattage any occupancy will have based off of a lot of code section requirements, etc. This is, like I said, the beginning of a much larger conversation that we're going to have. What this is, just 210:11 breaking down, is the number of circuits required in an occupancy residential is where we're focusing on, and that's what this section is talking about. Branch circuit required. So I'm just going to give it a quick read. All right. And I'm going to point out another code section, and then for those of you who want, look into this over today, and then tomorrow when we get in, we'll talk more about this, because we're going to have a lot of calculations here. I thought we'd get to this today, but we're not. So branch circuits for lighting and for appliances, including motor-operated appliances. Let's say the dryer is a motor-operated appliance. Garbage disposal, motor-operated appliances. Again, appliances, different types, blenders, etc. Shall be provided to supply the loads calculated in accordance with 22010. In addition, branch circuits shall be provided for specific loads not covered in 22010. So here's what I want you guys to do over today to tomorrow, is go take a look at Article 22010. All right, and give that a read. But what ultimately this is all going to boil down to is the number of branch circuits, the number of branch circuits required in a house. Okay? And like I said, this is the beginning of a much bigger conversation. So we'll talk about these tomorrow. We talked already about what is a circuit. We'll talk tomorrow about what is a circuit rating, and we'll get into determining the number of circuits you need in a house. Now, there's some required ones. This is where 210 comes in. For example, you have to have certain things in a house. You have to provide general purpose outlets for lights and TVs and general purpose things to get plugged in. Things that you don't know what the homeowner is going to have, but you have to provide, assume they'll have TVs and computers and things like that, right? So you have to provide these outlets. But since you don't know what they're plugging into this, you have to make a determination on the amperage of all of these things. And again, this is what takes us into determining how many breakers do I need to service all of those general purpose outlets in this house. There's some other requirements that you can, again, follow up and read today, and we'll follow up on this tomorrow, which are followed down here below. You can give these a read tomorrow. Houses have to have circuits for small appliances, blenders, air fryers, coffee makers. You have to assume they're going to put this into a house. By the way, this is all new construction. A 50-year-old house, you know, they didn't think of all the small appliances we have now. They didn't know air fryers were coming. So they might have less. Laundry circuits. Hey, I don't have a laundry. Okay, so that house doesn't get one. But if a house has a laundry, we have to consider the laundry circuits. Bathrooms must have. If you have a garage, there are mandatory garages as well. So give that a read tomorrow. We'll get back in here. I'm going to stop the video right there. You'll